Hey guys, it's Emma. Welcome back to my channel. In today's video, my friend Yuan and I will continue the discussion on causal inference in data science. Specifically, we will dive into pitfalls using regression discontinuity design and other forms of natural experiment, such as instrumental variables. I highly recommend checking out the video on RDD first because we will continue using the DoorDash example in that video to talk about pitfalls using RDD. Also, we will go over some of the best resources for you to continue learning causal inference after finish watching this video series, Causal Inference in Data Science. This video is the last video of this video series, and we have lots of things to cover, so let's get right into it. So thank you for walking us through the DoorDash example. So in that example, DoorDash used the RDD method to evaluate the impact of refund on customer lifetime value. I wonder, for RDD as a method in general, what are some things we need to pay attention to when using it in reality? What are some assumptions or pitfalls?
Okay, so the implementation that I showed you in the last tutorial is the most ideal case that you can imagine. In reality, like you said, there are many potential complications. So the first one is, how should we choose the bandwidth? Here, I kind of arbitrarily set it to 5 minutes and only considered orders that arrived between 25 and 35 minutes late. But you may ask, why 5 minutes, not 7 minutes or 2 minutes? So if the bandwidth is too wide, then we may include untreated and treated units that are not similar. If the bandwidth is too narrow, then we may not have many units that we can compare. So one way is maybe you're a domain expert, so you can use your knowledge to pick what usually works the best. There are like more data-driven methods, like based on cross-validation. You try out a bunch of different bandwidth to see which one gives you the best estimate of the treatment effect. And then another thing to watch out for is the assumption that we made. So in order for this to be a natural experiment, we kind of assume that the treatment is randomly assigned to folks around the cutoff. But sometimes this may not be true. For example, if you're a student and you're just about to get an A, so you may ask the teacher to round up your grade to an A. But if you're another student who got like 93.01, you won't ask teacher to round down your grade, right? So, and sometimes the rule makers themselves can change the cutoff. So maybe a university has a hard requirement on the lowest SAT scores for college admission. But then like a legacy student, maybe their parents donated a building to the university and then they really wanted to admit that student. And if their like scores are below the cutoff, then the university may change the cutoff to include that student. So this is another case where we cannot assume like random assignment. So that breaks this whole natural experiment setup. There are some issues that complicate the case that can be solved one way or another. One example is that sometimes the cutoff does not determine whether you get the treatment or not. So for example, when COVID vaccines just came out, so people over like 65 years old were first eligible for the vaccines. We can use age as a running variable and to see how that impacts people's immunity. Not everyone above 65 actually chose to get the vaccines. And then there are essential workers like below that age who were still eligible. So if we include everyone around the cutoff, do you think we will overestimate or underestimate the treatment effect?
Yeah. My understanding is that sounds like we are not even able to get the right estimate. It could. There are chances that it could be an overestimation or underestimation, right? because not all people older than 65 years old get vaccination. No? So what's the right answer?
We will underestimate the effect because for the supposedly treated units, some of them didn't get the treatment. And for the supposedly untreated units, some of them still managed to get it. So when we directly compare people around the cutoff, the treated units are diluted by some untreated individuals there. And the same can be said for the untreated, supposedly untreated units. The solution to this problem is something we'll talk about later. Here's a spoiler alert. So we estimate the probability of getting treatment based on age because not everyone like above that age will get it. So they only get it probabilistically. So we use the estimated probability basically to adjust for the underestimation. So the true treatment effect should be bigger than what we observe. So in the implementation video, I used linear regression to estimate the treatment effect. But sometimes the outcome may have nonlinear relationships with the rounding variable. Then we should use different types of regression rather than linear regression.
Mm-hmm. So previously you mentioned that RDD is one kind of natural experiments, right? Mm-hmm. So I wonder what are other forms of natural experiments other than RDD?
Yeah, so there are several, but let me just give you one other example that's pretty commonly used, which is so-called instrumental variables. So say we want to see if like years of schoolings may affect students' future incomes. As we talked about many times before, there may be like confounders like intelligence or family, socioeconomic status, etc., that might affect both like education attainment and someone's future income. Of course, we can statistically control for those confounders, but in this case, we can do better. So in the US, there's something special about the educational system. I don't know if it's true in other countries. So in the US, every kid is required to go to school the calendar year that they turn 6, but they can leave high school the day they turn 16. Let's imagine like two students like Bob and Mary. They are born in the same year, but Bob was born on January the 1st and Mary December 31st. Both of them will be required to go to school the same year, the same September 1st. 10 years later, Mary would be able to leave school on January, but then Bob has to remain in school the same year, like on December 31st. So just because Bob was born in a later season, he is required to stay in school for almost a year longer. But those are two extreme cases. There could be smaller differences. This variable, birth season, is really special. It has like some really nice properties. So first of all, it causally impacts the treatment variable. And then through years of schooling, it's correlated with the outcome, which is future income. And then it is unrelated to any confounders because no matter like how wealthy your parents are, it doesn't affect when you are born. But because of those properties, we can use this as an instrument. So what we can directly observe in the data is whether someone's birth season will affect the eventual outcome or not. That is something we can easily estimate. That's something we don't care about. What we really care about is how the treatment variables, years of schooling, impacts income. And this numerator is an underestimation of that because not everyone differs in years of schooling. If they finish high school, then years of schooling should be the same, regardless of the birth season. So the instrument only impacts people who drop out of high school. So we can use this instrument to estimate how much it impacts the treatment. So this is not what it does exactly, but conceptually, you can think of this as using birth season to estimate how long they will stay in school, and then use that to adjust the underestimation that we made in the numerator, so that we get an estimate of how much the treatment affects the outcome. In reality, it can be really tricky to use this method. First of all, not everyone is impacted by the instrument. If you don't drop out of high school, then you're not impacted by birth season. So this method may not be effective if like very few people are impacted by the instrument. And also, even if there are many people impacted, but they may not be representative of all high school students. So maybe for dropouts, schooling affects income differently compared to your average high schooler. And then a good instrument is really hard to come by. It is really hard to think of a variable that meets those standards. Like people used to joke that most of instrumental variables come to the mind of University of Chicago professors while they're talking in the bar. It's hard to think about one at work, maybe. So this is another type of natural experiment.
Yeah, thank you, Yuan, for explaining this. So we have learned quite a few causal inference methods in this series of videos, causal inference in data science. Could you give us a quick summary of what we have learned so far?
I've talked about 6 different methods in this series. It all began with this question: why is it important to know why? I think the answer is that if we don't know why something happened, then it's hard for us to change it in the future. For example, the example we used before was if like users behave in a certain way that we don't want them to, then figuring out factors that lead to those behavior will help us reshape user behavior. Even though we've talked about all those fancy methods, but I want to re-emphasize that randomized controlled trials or A/B testing is still the gold standard for figuring out the causal impact of maybe a feature or a product on some sort of metrics that you care about. So if you are able to run an A/B test, it is the cleanest and the easiest way to do causal inference. But sometimes it's not always like possible or feasible to run a randomized controlled experiments. And that's when life gives you lemons and then you need to squeeze some lemonade out of it. Sometimes we may get lucky. Even if you don't run an A/B test, the universe does it for you. So by creating some sort of cutoff after which the treatment is assigned to some units, but before which the treatment is not assigned, then you can take advantage of that scenario using regression discontinuity design. Or in the case of instrumental variables, if you have a good instrument, then you can take advantage of it to do causal inference. But natural experiments are really hard to come by. So sometimes we need to use some sort of statistical control to rule out alternative explanations. Here is an example from a very well-written paper that I recommend everyone to read. So basically, it's similar to the examples I've seen before. What we care about is how education impacts income, but then intelligence is a confounder that may affect both education and income. That influence may be direct or indirect. So intelligence may impact someone's grades, and then grades impact their education. This kind of variables that can affect both the treatment and the outcome are called confounders, and they are also called backdoor path. So statistical control basically blocks those backdoor paths. So here, we don't need to actually control for both grades and intelligence, because if you control for intelligence, it also blocks the path from intelligence to grades. We talk about that we can use regression to control for the influence of intelligence if we enter intelligence in the same model as the treatment to predict the outcome. And then we can also use matching. We can match students who are similar in terms of intelligence, and then compare how their incomes might differ. Sometimes we may be out of luck when it comes to regression or matching, because we don't have many treated or untreated units that we can compare. So sometimes when like a policy takes effect, it will affect an entire city or state. So in that case, we can use methods like difference in differences or synthetic control to create a counterfactual world where the treatment didn't happen, and then compare that to reality to see the impact of such policies or product changes. So that is a summary of this series. So I want to point out that this series is not meant as a comprehensive guide of how you can implement those methods in great details. It's more geared towards people who are interested in causal inference but may be intimidated by like 1,000-page books, and they just want to find a good place to get started. I hope like through this mini series we achieved that purpose. And yeah, and I guess that's everything.
Yeah, thank you for the summary. So speaking of comprehensiveness, for our audience who wants to continue learning more about causal inference, could you recommend some resources?
So first of all, I have to confess that I am not an economist. So maybe like many of you watching this, I also learned those methods by reading books or listening to talks in the past couple of months. Here are the ones that I recommend. So this is also taken from my blog post. So yeah, if you want to know how causal inference is used in fields like econometrics, I highly recommend this book. But this book didn't talk about more recent methods like synthetic control, and didn't talk about how we can use directed acyclic graphs to represent causal relationships. The last three books are also in an econometric tradition, and they went into great details about those more recent methods, and they all have examples for how you can implement those methods in different languages like Python or Stata. And if you're interested in the computer science side of causal inference, then I recommend Causality by Judea Pearl. And then if you want to get a quick overview of this field, I recommend like the Book of Why, which is a popular science version of the causality book. There's some lovely short review papers that introduces how you can use different quasi-experiments, so including regression discontinuity, synthetic control, so in academia, in industry, and there's also a lot of companies like DoorDash or Uber and Lyft that frequently use those methods that have like some great blog posts or talks about how they use those methods for their business cases. Here, out of curiosity, I found a syllabus, and if you look through the syllabus, the structure is pretty similar. So they started with like the philosophy of causality, which in this case is pretty much based on counterfactuals. Then they talk about graphic models, which is directed acyclic graphs, and how we can use that to represent or think clearly about causality. Later on, there are things that we didn't talk about. People may ask, where do the DAGs come from, right? Like, how do we know which variables are important and how they are connected? How we learn the causal structure of variables is called like causal discovery, and then there are a lot of formal methods for doing that, which we didn't get to cover in the series. I think these are pretty good places to get started, but then causal inference is such a broad field. I think each of those methods may be like a whole semester's worth of lectures. So just start with what's most relevant, like to your work, to your business problem, and then go from there.
Yeah, sounds good. Thank you so much for sharing these resources. Alright guys, thank you so much for watching. If you like this video, make sure to subscribe to this channel to get updates about future content. I will see you soon.